Thank you very much. It's a pleasure to be here today. I wish I could have come for the whole week, but personal things get in the way sometimes. I'd like to start by saying that in Chicago, we were working very hard to have this ICAP come to us this year, and I can see just from the few days I've spent here that Joseph did a better job. So thank you for putting together a wonderful conference, Joseph, Michaud. So I appreciate you guys. So I'm going to tell you about work going on in my group and in collaboration with Dave Schuster's group, where our focus has been on multimode cavity QED, and well, indeed, just cavities in general, but our focus today will be on the cool physics you can see when you insist on studying more than one cavity mode at a time. So there are sort of three stories I'd like to tell you here, and what's kind of wonderful is that these first two overlap quite a bit intellectually with some of the techniques Marcus told you about. I'll tell you about making two photon Laughlin states, and then making fluids and solids out of microwave photons. And so seeing sort of the similarities and differences between the ways that we prepare these states, the way that we characterize these states, from the way that this work takes place in a quantum gas microscope, I think is quite beautiful. And then at the end, I'm going to tell you about some work that we just put up on the archive last night, actually, where we've now demonstrated quantum-limited transduction of millimeter wave photons into optical photons with about 60% efficiency, hundreds of kilohertz of bandwidth, and less than 1 photon of added noise. Okay, so we've got a lot to get through, so let's put the most important slide first, in case we don't make it. We're going to try to make it. I have an hour. Is that correct, Joseph? Nobody has any flights to catch? Okay, great. So these really are the folks who have done all of this work. I should say I've moved to California. My group is still in Chicago. So it's very clear that I'm not the one doing any of these experiments. I'm sitting in the sun getting tan. Not really that tan, I just burn, but you know. Anyway, so thanks to all of them for really doing a wonderful job on this. And feel free to reach out to me or them afterwards if you have questions. So with no further ado, let's hop in. I'm going to first tell you about how to make Landau levels for light, how to make photons interact with each other, and how to kind of put those ingredients together to make Laughlin molecules of light. Okay, so the central premise of this story is that a photon in a multimode cavity looks like a massive particle in a harmonic trap. So what's the picture you should have in mind here? So I've got two cavity mirrors. I send some light into this cavity away from the axis. And my claim is that if you watch that light inside of the cavity, if you could do that, it would oscillate back and forth transversely like a massive harmonically trapped particle. So this connects to some ideas from Martin Weitz and from exciton polariton experiments, if you're familiar with those. But in case you aren't, the way you should think about this really is just trace a ray around in this cavity, and you can watch as it moves along the cavity axis, it bounces back and forth, and the curvature of the mirrors kind of redirects the path and keeps the photon from running off to infinity. And if you just watch in the middle, it looks like this massive harmonically trapped particle. And lest you worry that this is really sort of hand-wavy, let me point out that the eigenstates of a quantum harmonic oscillator are Hermite-Gauss in space. And if you've ever computed the modes of a laser resonator, just a Fabry-Perot cavity, in fact, those are also Hermite-Gauss in space and uniformly spaced in energy, just like the harmonic oscillator eigenstates. So there's a nice formal mapping between these two, and so you can really understand this quite formally. It works out. So if I were to send light into a cavity off-center, I could write that light as a superposition of, say, the lowest mode and the first excited mode. They have some difference in energy here. So a little bit of time later, that plus sign becomes a minus sign, and now the light is off-center in the other direction. Okay, so the picture you should have in mind is that my light is oscillating back and forth transversely and exists everywhere longitudinally in this cavity. If I want to add a magnetic field to this story, we should take a brief moment to think about periscopes. And the picture you should have in your mind is that if I look at a tree through a periscope, if it was vertical at the top, it's vertical at the bottom. And the first thing that your PI told you when you joined the lab is don't rotate the top mirror with respect to the bottom mirror of your periscope. And there are all sorts of reasons why, but a simple one is that the polarization gets rotated, the image gets rotated when you go through this periscope. And so the interesting thing is that as I rotate the top mirror with respect to the bottom mirror, that image just rotates. And so now the idea is if I take a cavity, make it out of 4 mirrors, and I twist it out of the plane, then every time I go around this cavity, my image gets rotated a little bit, or my ray path gets rotated a little bit. And so you should now think of this as turning the lab frame into a rotating frame, okay? And so what we know is that when we live in a rotating frame, we get Coriolis forces and centrifugal forces. And this Coriolis force is omega cross P, which is V cross B. That's a Lorentz force. Great. So we've generated a Lorentz force for our photons. And we've also generated this centrifugal force, which is like living on top of a bowl. It's a radially outward force that increases the further out you are. And so the idea is we can just compensate that with our harmonic trap, which we generated from the curvature of our mirrors combined with the length of our cavity. So to make a long story short, okay, we can tune to a point where the harmonic trapping exactly cancels that centrifugal force. We get these modes to be degenerate, and it turns out that when you make these Laguerre-Gauss modes degenerate, that's equivalent to a lowest Landau level, right? So there's this beautiful connection between the modes of optical cavities and massive harmonically trapped particles now in magnetic fields, okay? If you zoom in on this point, you can see we can make the modes degenerate to within a couple of megahertz, which is in fact good enough for the next thing that we need to do if we want to study many-body physics, which is to add Rydberg EIT to our story to make the photons interact with one another. So I'm not going to go too much into the details of how that works. And by I'm not going to go too much into the details of how that works, what I mean is that's all that I'm going to say about that. If you want to hear more about it, we've got a number of papers on it, and I'm happy to chat with you afterwards. But let me describe what I think is a beautiful Gedanken experiment that we've pretty much realized in the lab. This idea comes from Jacopo Carusoto, and it's an alternative approach to building Laughlin states to what Marcus told you about earlier, okay? So imagine I have photons that interact with one another locally in space. Now, if I look at the modes of my cavity in the presence of these interactions, well, the modes, as I said, were these Laguerre-Gauss modes of the lowest Landau level, okay? If I send a photon into the lowest mode, it'll just go through the cavity. It has nothing to interact with, right? No problem. What if I send a second photon in while that first one is already in there? Well, what you'll see is that that second photon would repel the first photon, and so the energy of that 2-photon state is more than twice the energy of the 1-photon state, and so that second photon cannot enter the cavity, okay? And so as a consequence, that photon will just reflect off, okay, and we'll only get 1 photon out of the cavity at a time. So this is single-mode physics, and I promised you that we weren't going to talk about single-mode physics. So I apologize for that, but that's all we're going to say about it, I promise. Well, okay, I have to say one more thing, which is that an experiment of this sort was first done by Jeff Kimball with a single atom in a cavity, and that worked beautifully, okay? What I want to describe next, I think, is a little bit more bizarre. What happens if I send light into the L=1 mode of this cavity? Well, you might say it should be the same story. If I tried to put 2 photons into that mode, they would repel each other, there would be an energy shift, and I wouldn't be able to get 2 photons into the cavity. But here's the thing that's beautiful. 2 photons in L=1 can actually collide with each other and conserve both energy and angular momentum and turn into a photon with 2 units of angular momentum and a photon with 0 units of angular momentum. So now the question that we need to ask ourselves is there some superposition of 2 photons with 1 unit of angular momentum and 1 photon with 0 unit and 1 photon with 2 units that has actually no interaction energy between the photons? Can they somehow become correlated and avoid each other by going into a superposition of those 2 states? So the answer is yes. The state looks like this. This is what we would call a 2-particle bosonic Laughlin state. And the upshot is that that particle minimizes the interaction energy of the 2 photons, or the 2 bosons. And so what we would expect to see is we send in these photons with 1 unit of angular momentum, and what we get out is a correlated state where sometimes they both have 1, sometimes one has 0 and one has 2 because of these collisions. Okay, so let's see if we can keep ourselves on track here. I swear I'm not texting here. I'm just trying to keep my timer going. Okay, maybe I'm texting. No. Okay, so experimentally, how do we do this? We build this topological photon collider, if you will, and we send photons in with angular momentum, and then we measure what comes out of the system, okay? So if we send photons into our lowest mode of this system, and we look at the correlations of the photons coming out, well, what we see is the photons sort of avoid each other in time. If we just got 1 photon at time 0 here, the probability of getting another photon is low for a time given by the lifetime of these photons in the system. By contrast, if we put in photons with angular momentum, they can collide and come out in pairs, and so we see that actually this suppression to 0 kind of is reduced. The photons can come out at the same time. And indeed, if we look at the correlations between these photons, what we see is we send photons in with some angular momentum, and they come out in these other pairs of modes correlated in their angular momentum. So this is a subtle story. In practice, in our cavity, the modes are not quite degenerate, and so what we end up doing is actually flow-K modulating the system to make them effectively degenerate. I don't want to say more about that, but you can certainly read more about it in our manuscript. Let me just conclude this part of the talk by saying we're hard at work on developing the next iteration of this system, which relies upon lenses inside of the cavities to reduce the aberrations. And so what we have here is a cavity to build up the power of our blue dressing beam, and it is overlapped with our physics cavity, which goes that way, and that's a SNOM tip that we use to co-align them. Okay, so that's story number 1. The second story that I'd like to tell you is about making fluids and solids out of microwave photons. So let's just hop right into this. I know that this is an AMO community. Joseph may kick me off the stage for talking about microwave photons, but you know what? They're light as well, and AMO is okay, I guess they're not really optical light. Fine, I take it back. So this is a collaboration with Dave Schuster's group, but let's take a moment here just to talk about how we would even make a lattice for microwave photons, because I want to make a Bose-Hubbard model for these microwave photons. So what makes a good lattice site for holding microwave photons is an LC circuit, okay? Or an array of LC circuits. So the problem with making a lattice site out of an LC circuit is that the photons don't interact with each other. That is to say, if the resonant frequency of this circuit, 1 over root LC, is 4.5 gigahertz, then when you put in your first photon, the requisite energy is 4.5 gigahertz. For the second photon, it's also 4.5 gigahertz. There's no Hubbard U, there's no interaction between the photons. So what we need is a nonlinear inductor, that is an inductor whose inductance depends on current. The simplest object you can put in that does that at the single photon level is a Josephson junction. Without saying more than that, you can now understand this system as if your first photon, that goes into this resonator has to have an energy of 4.5 gigahertz. The second one, to be resonant, needs to have an energy of 4.2 gigahertz. So this is an attractive interaction between my photons of about 300 megahertz. Okay? And now if I want to have tunneling in my system, what I should do is take two of these resonators and couple them together with capacitors, and I can have any amount of tunneling that I want. So we're going to pick 300 megahertz of interaction, 10 megahertz of tunneling. This is in the strongly interacting limit. And the question you should ask yourself now is, how long do the photons live in the system? Well, typically for 40 microseconds, thereabouts. The world records are like 500 microseconds. But this means that the photons can collide like 12,000 times or tunnel 400 sites within their lifetime, which is pretty compatible, actually, with what we realize in Bose-Hubbard systems with cold atoms. So physically, this is a micrograph of our system. These are the transmon qubits. This is our quantum gas microscope, if you will, that allows us to read out the occupancy in photons of each qubit. And then we have drive lines for exciting the various qubits. So if you want to make a Mott insulator in this system, remember we can't do this superfluid Mott insulator transition where we vary the depth of the lattice. And anyway, the natural resource for us is really not a Bose-Einstein condensate, so that kind of an approach wouldn't really make sense. So how do we make a Mott insulator of photons? Well, imagine I had an object on the left that always refilled itself with a photon whenever it was empty. It just created one out of the vacuum. If I coupled that to my system, well, then what I would expect to happen is that photon would tunnel in, and then the site would refill itself, and nothing would happen, right? Because there's some interaction energy cost to them being on top of each other, which is larger than the tunneling energy. But as soon as that photon hops over, another one can hop in, and so on and so forth until the system is filled up with photons. Okay? And so there's a whole theory of this kind of an idea. It turns out building this object requires dissipation. We call this reservoir engineering, dissipative stabilization of many-body states. Okay? And these references from various groups talk about this at levels from sort of very broad and formal to our manuscript here, which is a very concrete explanation of how one might do this. Okay? So I've told you how to make this piece. I haven't told you how to make that piece. So remember, this lattice of transmons is this piece. What is that object? Well, I need something that whenever it has 0 photons, refills itself with 1 photon. So that's like making an inversion, right? If you just think of this as an atom with 3 states, I want to make an inversion in this first excited state. So what I need to do is excite it up to some second excited state and make sure that second excited state decays down really fast, right? So if you're going to make a gain medium, well, you don't make the gain medium. You just pick the right gain medium, right, that has this property for the pump laser that you like and so forth. The cool thing we can do is we say, oh, we want rapid decay between those 2 states. Well, what's the energy of that transition? Let's make an RLC circuit at that energy, capacitively couple it to our transmon, and it's going to damp only that transition and make that decay fast. Okay? And so this is sort of the beauty of circuit QED. We combine these ingredients. So what I'm going to show you here is the occupancy of each site in a lattice with this stabilizer at the right end. We start from empty, and over a microsecond or 2, the system fills up to 1 particle per site. Okay? And then you can ask yourself, well, what happens if I get rid of a particle here, which we can do with just a pi pulse to take a photon out? Well, if I don't have my stabilizing drive on, now I have a hole that random walks back and forth through the system. If I do have my stabilizing drive on, the hole random walks across once, gets eaten, and we're done. So, this works beautifully. We think these ideas could also work for stabilizing sort of any incompressible phase of matter. But what I'd like to tell you about briefly is how one might stabilize a fluid, or how we did stabilize a fluid, how we built a fluid. So the challenge here is that you can't stabilize a compressible phase of matter with this technique, because then each photon costs slightly more energy than the last to put in. There's no sharp gap where it starts to cost a bunch more energy and this filling site will stop filling. So, but what we do have instead at our disposal is the ability to pi-pulse particles into our system, okay? The ability to tune the energies of the individual lattice sites, and this site resolve detection. So can we combine these abilities to prepare a superfluid? Okay? So let's warm up by just trying to prepare single particle eigenstates of a degenerate lattice. So the idea is, imagine I start with disorder with my lattice sites staggered at different energies, and I put a particle into this site. If I then adiabatically ramp the disorder to 0, well, that should adiabatically connect me to this lowest quasi-momentum state. And similarly, if I put a particle into the second lowest energy state, or site, I'll make this second lowest quasi-momentum eigenstate. So experimentally, we can do that. We put a particle into this highest energy site, and then we ramp our disorder from large to 0. And you can see the particle delocalize in this uniform lattice. And this is data. Indeed, we produce that lowest quasi-momentum state. Similarly, if we put the particle into the second lowest energy eigenstate of the disordered lattice, we get this second lowest energy eigenstate in the ordered lattice. And this is quite neat because it gives us a way to index our eigenstates and prepare whichever one we want. Okay? Before I go into how we do that in practice, I'd like to point out a tool that we use that I think Marcus also told you about, which is the adiabatic ramp to degeneracy and back. And this is a really wonderful, powerful tool for characterizing entropy generation, because in the disordered lattice, any particle that doesn't go back to its initial site is added entropy. Right? And so when you have some complicated entangled state, it's hard to measure how much entropy you've generated, how far you are away from the ground state. But when all of your eigenstates are localized, you have this wonderful tool, which is single site resolved microscopy, for directly measuring entropy generation. So this is just showing, as a function of ramp speed, how likely the particle is to go back to its initial site. So for the very fastest ramps, it's very likely to go back to its initial site because we didn't give it time to move at all. Okay? And then in between, that probability goes down. You have some diabatic crossings. And then for the slowest ramps, you go back up towards unity. I would point out this is 3 decades of time here. And so at the very longest times, you can start to see the decay of the photon from the lattice. Okay, so we can now perform these experiments with 2 photons initially, making this 2-photon fluid, or 3 photons, or 4 photons. It works just beautifully. We can look at the correlations between these photons, and indeed, when we rescale by the density, it agrees very nicely with a continuum sort of Tonks gas story. We also measure the purity of the single site density matrices, and that tells us about the extent to which the sites are entangled with one another. So in the localized phase, that is to say when we've got this stagger, no matter what your density is, you have fairly good purity. In the delocalized phase, when we have this Tonks gas, the sites are entangled with one another, and so in fact you have the most entanglement near half filling, because in that situation, the occupancy of one site tells you the most about the rest of the lattice that it possibly can. Okay, but this raises an interesting question, because we were picking which manybody state we were generating by pi-pulsing particles into the system, right? Pi-pulse, we make these states. We pi-pulse another particle in. We made that state. We pi-pulse a third particle in. We make that state at degeneracy. But my question for you is, what happens if I put a pi over 2 pulse here? Well, now I've made a superposition of 2 fairly different eigenstates, right? Half the time I had a photon there, half the time I didn't. And at degeneracy, I generate this fluid, which is a superposition of the two that I generated for those two states. So the question I'd like to ask is there coherence between those two states? And is there a way to cleanly detect that coherence in the localized basis, rather than just by looking at dynamics in the system? So the experiment that I just showed you, where we showed that final state, was just generating that superposition. But instead, I could drive a pi/2 pulse, adiabatically ramp to degeneracy, wait some variable time, adiabatically ramp back, and drive another pi/2 pulse. Okay? And then, as a function of that hold time, see what I get. So this is kind of what that experiment looks like schematically. And when we do it, we see Ramsey fringes. And so you should think of this as mapping all of the coherence of these two manybody states onto information in a single qubit where we can see that coherence. So this is showing those fringes as a function of increasing ramp time, and this is in the Fourier domain. So this is for a superposition of 0 and 1 particle. For very fast ramps, you generate superpositions of all the eigenstates, and as you go slower and slower, you eventually just generate one eigenstate. And similarly for 1 and 2 and 2 and 3. Okay. So the last thing I'd like to tell you about in the last 25 minutes of this talk, I'm just kidding, take it easy, Joseph. So I've told you a lot about quantum circuits, and so you might ask, are they a good tool for quantum communication? And the answer is, microwave photons are terrible for quantum communication because at room temperature, there are thousands, if not tens of thousands, of black body photons at 10 gigahertz, right? So we would need some way to coherently convert these microwave photons into optical photons and back. Don't take a picture of this slide. It's just a cartoon of a turtle and a person crossing a street. Okay, so the last thing I want to tell you is about a collaboration with Dave's group, where we've made a cryogenic transducer, in this case for converting optical photons to millimeter wave photons and vice versa. Okay, so what is our transduction scheme? Well, we want to convert an optical photon to a millimeter wave photon, or vice versa. So step 0 is you need an optical cavity and a millimeter wave cavity. Okay? And then you need to put something in them that can bridge the energy difference between those modes, and that'll be rubidium-85 atoms. We picked 85 because we weren't sure how many we would be able to trap in our crappy cryogenic MOT. And so 85 has a higher isotopic abundance. Seemed like a good choice. Great. So let's follow an optical photon around as it goes through this system. So the photon goes into the cavity, excites an atom to 5p3/2. Then we need to shine a laser at 481 to excite the atom up to the Rydberg state. Well, why do we want to excite it up to the Rydberg state? Because there's a Rydberg transition resonant with this 100 gigahertz cavity into which the atom can now emit the photon. Okay? And then we can de-excite this atom back to the ground state to erase any quantum information in the atomic cloud with this 297 nanometer beam. So I'm skipping absolutely everything about phase matching, everything about cooperativities, collective enhancement, so forth. The only thing I want to add is that this is a very weird cavity. Why did I draw a cavity as just a hole? 2 holes in a block of niobium. You should read Aziz's paper. It's beautiful. But the upshot is that we characterize this system without the millimeter wave cavity. We get a dark polariton in the middle here. We can split it with classical millimeter waves. When we tune the millimeter wave cavity to resonance, we get Purcell broadening of this cavity, of the EIT line, basically coming from a combination of the millimeter wave vacuum and about half a millimeter wave thermal photon. And we can also drive the UV transition and start to see Rabi oscillations. When we put all of that together, we see about 60% conversion efficiency with a bandwidth of a couple hundred kilohertz, 300-ish, about 6 0.6 photons of added noise coming from the finite temperature of the cavity. We're at 5 Kelvin. So this works exactly as the models say that it should. We have a lot of confidence that we know how to push forward on this. The upshot is moving from 5 Kelvin to 1 Kelvin will reduce our added noise to about 0.01 photons. Our conversion efficiency is actually limited by our 480 nanometer Rabi frequency, so a colder, denser gas will solve that. We're playing with ideas for going to 10 gigahertz, just with a bigger cavity, microwave. But Dave's group is also developing 100 gigahertz transmons. An amazing thing is when we go from 5 Kelvin to 1 Kelvin, the single atom cooperativity goes up to a few thousand. And so this puts us in a regime where, in collaboration with Monica's group, we're very hopeful that we're going to be able to have the cooperativity larger than the atom number and Heisenberg squeeze the atoms on this millimeter wave resonance. So with that, thank you, Joseph. Thank all of you for your attention. It's a pleasure to be here.
Thank you. Question, June. And then Jakob.
John, thanks for the exciting talk. I have a question going back to this, L equals 2, L equals to 1 photons converting to L equals to 0 and then L equals to 2. My question is why that conversion efficiency is not 100%. If it's avoid crossing, then in principle, you can dial this, can completely convert. And is that reason because you have to do Foucault engineering, because your cavity is not degenerate, as you explained, and then the Foucault engineering can be tuned. There's some Rabi frequency which is competing with there's a crossing there, and there's a photon interactions that will govern this efficiency of the conversion.
So I think there are two different answers to your question. The short answer is it shouldn't be 100%, and the reason is that I'm looking at the transmission through the cavity, and the Laughlin state, which is the state with zero interaction energy, which is the one that's resonant, is a superposition of 2 photons in L equals 1 and 1 and 0 and 1 and 2. So in fact, if I go into the mode at 0 energy, it should be a superposition of those two, okay, and not a conversion. But you've hit on another important point, which is, it turns out that doing this topological physics is just orders of magnitude harder than I think I expected it to be. It's much harder than Marcus expected it to be, right? So we're now trying to go to a system where the performance is really what we want. The Foucault engineering adds all sorts of complexities that are, again, in the manuscript, but brushed under the rug here. And to really push this field forward, I really think you need a custom designed cavity. So that's what we're doing next.
Thanks.
Yeah, hi John. I'm here. Amazing stuff. So I have a question about these coupled transmon cavities. I used to think that in that kind of circuit, when you have many coupled cavities, the problem was that the resonance frequencies are never really identical, and when you make them identical with additional electrodes, then your coherence time goes down. So how did Simon Schuster solve that problem?
So. Let me start by saying this, at some level, the challenge of control is the thing that makes, I think, transmons most challenging, okay? So the way you tune the transmons is by applying a magnetic flux. I drew them as though there was one Josephson junction. In fact, each transmon has 2 Josephson junctions, and there's a flux loop, and you feed some magnetic field through it. The way you get the best diagonal control, that is to say the flux loop for transmon J only tunes transmon J, is by putting that flux loop as close as possible, the bias loop as close as possible to the flux loop on the transmon. The problem is that then you can get loss through that loop. So then you can play games, okay, add a Purcell filter. The simpler solution is to move the flux loop a little further away. Then you get all kinds of crosstalk between your transmons, and you measure it. We call it a confusion matrix for the obvious reasons. And then you use fast control of all of your things in parallel with these known transfer function, which is frequency dependent and amplitude dependent and everything, to get independent control of the objects. So in fact, the reason it's taken us a while to go from this dissipative stabilization, where you just make them resonant and dissipatively stabilize the state, to a place where we can controllably move things around in real time, is because building up the understanding and technology to make that happen is very, very challenging. And I have to say that's really a testament to the team over the last 2 years. I think I didn't even fully appreciate how terrible of a task that is to make sense of until I read the supplements of the manuscript. Typical PI, right? You're just like, where are my results? No.
Is that scalable?
So what I would say is, I think there's some question. Okay, so what's the long-term solution? A long-term solution is bump bonding. Okay, you can reduce the crosstalk by having a second ground plane above your sample. Okay, the challenge is, how do you make good electrical contact to that ground plane? And there are new technologies available that make that very easy. We have historically made our own chips in a nanofab facility, and the bump bonding is a pretty involved process. So my impression from a little bit afar is that we can do it. The really cool thing now on the circuit QED side, do we have anyone from Lincoln Labs here? No? Well, big shout out to Lincoln Labs. Lincoln Labs has a foundry, and the way it works is if you're in with them, it's like a PCB. You design the board, and then they make it and send it back to you. So I think a lot of these challenges are going to be resolved by these sorts of NQI, large funding scale things. I think the circuit people are making very good use of those resources. One question in my mind is, how do we make better use of them? But that's a question for another day.
Amazing talk. Thank you so much. Since your transmons are part of a circuit, do you have access to the conductivity? And would they may have a signature of your photonic states that you generate in there?
That is a very cool question. So this is a technology that we would like to build up. Basically, you need dissipative coupling at 2 points, or maybe you could do it at 1, as I'm thinking now. We have dissipative coupling, right, because we're coupled to this reservoir through that resistor. And so I would say we haven't yet come up with the sort of awesome experiment to do along those lines. If you have ideas, I'd love to chat about them, but I think that's a really fun direction.
Great. Thank you.
So I want to ask about the experiments where you started with a lattice of circuits, and you introduced disorder, and then you excited a single one of those things, and then adiabatically removed the disorder, and ended up in a block state. Okay, so now if I've understood correctly, yeah, there you go. So you excited the highest single particle localized state, and then you adiabatically transformed into the lowest quasi-momentum state. Why didn't you go into the highest quasi-momentum state?
So that's a great question, Bill. I think there are two answers here. One is, could you tell the difference between the lowest quasi-momentum state and the highest quasi-momentum state? I'm plotting probabilities.
Okay.
So the amplitude for the highest one, they just swap sign back and forth.
Yeah.
Right?
Okay, and
So-
you lose the sign.
So you lose the sign. But then why did I call it the lowest quasi-momentum state? Well, you have to go through this very carefully, but if you want to have a minus j, a dagger I, a I plus 1 term in your Hamiltonian, you need to couple with inductors, not with capacitors between your lattice sites.
Yeah.
And we coupled with capacitors.
Oh, I see. So you've built in a phase change that looks like a high quasi-momentum.
So
into
our
the low
dispersion,
quasi-momentum.
instead of looking
Okay.
like this,
Okay.
looks like that.
Okay, I got you.
All right. Thank you. Let's thank Jonathan again.
Thank you.